Good morning. Good morning, everybody. We are here, the group of people that are involved in this seminar that we have organized concerning ARIES. ARIES has been for a long time an interest of our research group. We have been exploring the potential of these platforms for several years. We have signed a memorandum of understanding some years ago between the Basque Center for Climate Change and Ca' Foscari University. More recently, thanks to the establishment of a new program on climate change adaptation at FEEM, we have made this collaboration more concrete. And we have started some joint activities. So it's very nice for us today to have the opportunity to have here, I would say, the core team of the ARIES platform. And so I will immediately give the floor to the BC3 colleagues. Today we will have with us Ferdinando Villa, Stefano Balbi, and Greta Adamo, who will contribute to this seminar that I hope will be quite informative to let us everybody understand what ARIES is and what are the main potentials of this platform. So I leave the chair and the floor to Ferdinando. Thank you, and I'll see you probably later. Thanks.
Thank you, Carlo. I'm Ferdinando Villa. It's nice to meet everybody, although meeting people this way has become a little bit of a disappointment compared to the old way. I am Ferdinando, so I am the founding father of the project, so I get to do the introduction, and but it will be a very choral talk. It's going to be a little bit more of a technical seminar than the one that we normally do, because we have people who are researchers online. So I'm going to be very quick on the introduction and try to give you the general idea and the reason about why this project exists. And then we'll go deeper into the way we actually make it exist. The idea from the start is, let's say, we all talk about open science these days, which took a long time to actually become part of the scientific narrative. And it is mentioned, it's not necessarily done, which is usually the case in science. People talk and they're happy with that. We are taking the other route. If we haven't done something, we don't want to talk about it. But open science is one thing, but the rationale for this project to exist is something that I've believed for a long time, which is the problems of this world as a way too complex to fit in one brain at a time. Particularly if you consider the disciplinary perspective, or even in any other situation, one brain can be very much, one person can be very much an expert in something. No person is an expert in everything, and no problems like sustainability, etc., that actually affect the complexity of the world can be solved by one person at a time. The problem is that a system has to fit in one brain in order to be predicted. At least there is this collective delusion that if you put 10 of the best experts in a room and you give them an incredibly complicated problem, somehow the solution to that problem will emerge from that room. But the problem is people speak different languages, people don't have one brain, it's still 10 brains. So this project is trying to use artificial intelligence as the bridge, to build a bridge between human intelligence, human competence. So it's a very different way to use artificial intelligence than what is popular today. Most of what you hear today about artificial intelligence is basically extracting knowledge in human comprehensible form from large streams of data. What we do, I'm sorry, I still am under the weather a bit. What we try to do with this project is to use artificial intelligence as an aid so that knowledge from humans expressed in human terms can be encapsulated, described, and put online, both data and hypotheses, models, equations, etc., which we see as basically the same thing from the point of view of the system. can be put online, and then we can ask a very complicated question that requires multiple brains to be solved, and it doesn't fit in one. And a machine can try to find all the different components of knowledge that are necessary to respond to that question and connect them. And by using semantics and artificial intelligence, we try to do it in a way that is automatically valid and validated, and can actually validate itself and learn from the usage of the machine, so that higher level knowledge can be built from lower level, but still hard to achieve expert knowledge. So, question? Yeah. Okay, thank you. So I have these infographics here, and I have 5 slides, but I want to go very quick because we want to go to the details as soon as possible. This one kind of encapsulates the 5 dimensions, I think it's 5, 6, of the vision that we try to enact in ARIES and in our activities. We realize that knowledge, scientific knowledge, but not just scientific knowledge. I mean, scientific knowledge exists for thousands of years, and our brains have certain limitations. Now we have mathematics, we have computer science, so we have a better way to communicate knowledge. But there is indigenous knowledge. There are a lot of things that are known to humans since a long time. As I usually say, the book of knowledge that we need in order to save our future, or to depict a sustainable future, has been written already, and for many times and in many ways. What we are missing is the ability to read this book. And what the machine is trying to do is trying to take all these pieces of knowledge and give us an instrument so that this book can be read, basically. So access to knowledge is one thing, and we try to turn the unequal access to knowledge, which is getting worse and worse because knowledge now is being monetized, is being basically a part of the capitalistic system. You think about how much you have to pay to publish a publication or to read it. And if you are underrepresented nations, you can basically cannot do it. Try to turn that into fair access. Policies that are not informed by science, for all of these reasons, for the lack of transparency, etc., can be based on knowledge and nature and what we know about the world. The compartmentalization, which is the typical paradigm for all the disciplines and even regionally, can be turned into a much easier to access science. The black box paradigm that turns knowledge into basically silos can be turned into a transparent way to communicate. Very important today. Much of the research is oriented to the industry and comes from the industry, and we by producing a mean to use knowledge as a key and retrieve it from online systems, we can basically put the knowledge back into the hands of society. And more interestingly, because we are talking about artificial intelligence, we can use it in a virtuous way. Today is not being used in a virtuous way. Basically, artificial intelligence is an instrument for the people who basically already own the world to keep owning it and to keep their control over society. But we realize the possible benefits of using artificial intelligence to enact a real democracy of knowledge, where knowledge is equally accessible to everyone, and no matter what it is, your level of decision making, or just a citizen or a scientist or a student, you have access to the same knowledge. Everyone has access to the same knowledge, and the ability of using it is unrestricted. So there are 5 slides here, but I don't think I want to go particularly deep here because I already described all of these things. I wanted to be quick so we can get to the point very rapidly. So I will come back and give you more technical details, but for the time being, I leave the floor to Stefano, and it will give you a more precise idea. So.
Hi, everybody. Thank you for being online. I am Stefano Balbi, and I'm in charge of the modeling activities of the team. So we have this nice introduction by Ferdinando on the vision of the project. And so why do we do this? Is, of course, from this slide, the main point is obviously there is a deluge of data out there, and the main thing is how can we integrate it for the benefit of everybody, for the benefit of the society. So we know there are multiple data sources, and they all are very important to solve multidimensional problems like sustainability and the Sustainable Development Goals, for example. So there are demographic data, national census, household surveys. Then there is obviously the remote sensing data, satellites and drones. There is crowdsourced information, ever more important. And here we don't talk about, for example, traditional knowledge, for example, from communities, native communities. And then there is the big data idea that at the moment many people talk about big data, meaning big data sets, even though big data has a different kind of meaning, including mobile phone data, social networks, and etc. But this is only, let's say, the data perspective. What if we take this a little bit a step forward and we talk about models instead of data? So if we want to, for example, have a representation of the planet and make like a digital twin of the planet, like is the objective of the European Commission with this destination Earth, is, let's say, a combination of the Green Deal and also the digital strategy of Europe. And so the idea is to make a digital copy of the planet itself. And how do we do that? Definitely, it's impossible to do it without a technology that allows to integrate all this information. Not only that, but it's also a technology that needs to integrate different kind of modeling techniques, and we need to cover all these aspects. So the biosphere, the atmosphere, the hydrosphere, and the geosphere are the planetary boundaries where we are living. And then there is also the macroeconomics, the microeconomics, and everything else ends up into waste. So we need to be able to have modeling components that allows us to represent all these components of the system and put them together. It's not easy, but we are suggesting here that we can do it. So an integrated technology has to have these advantages. One is to incorporate the best available knowledge. The second one is to combine different scientific products produced independently. The third one is important to track quality and uncertainty. And then it's important to integrate different modeling techniques, because there is no one model that can fit all the problem, but different modeling paradigms need to be integrated to resolve very complex problems. And then the issue of scales. So it's important that an integrated technology is able to cover local scales, global scales, and everything else in the middle. And finally, this is the main point that we want to talk about today, is to adopt a common semantics. So we believe that semantics is a part of artificial intelligence that is able to solve, let's say, the missing piece for integration. We have already described this vision in this article. The Global Environmental Agenda urgently needs a semantics web of knowledge. So now I will leave the word to Greta, that will explain why and how we use the semantics in ARIES.
Hello, everyone. Thanks for this introduction. I hope that my voice will work. So let's dive into the semantics. Now, Ferdinando and Stefano have been mentioned a lot, the word integration and also the word semantics. And I will start really from the beginning, what is semantics, just to be all on a common ground. And this is a very simple definition of semantics that you can find in literature. Most of the things that I will show you are based on the literature, and I inserted some like bibliographic references if you're curious to know more. So semantics is a field and is the study of the attribution of meaning to words and expressions. There are many theories out there, but this is, I think it's enough more or less to give like a very simple definition. No? So for instance, if we are saying the word, term cat, we might think, oh, what does it mean? That is very intuitive and could be, oh, I mean my cat, or I mean the definition of what is a cat. That is the attribution of meanings. Of course, it's very intuitive, but as I said, this is enough for now. No? In ARIES, this attribution of meaning is given using ontologies. What ontologies are? Ontologies, I will focus now on the computer science part, because ontologies is stem from philosophy and also is a very interdisciplinary area. Computational ontologies are basically informational artifacts that specify the meanings of terminologies, vocabularies, in order to create a common understanding, an explicit understanding of what we are talking about. Okay, that is, I would say, not easy, but a basic definition of ontologies. But we will see more specific what does it mean, and also why do we need that, no? Why it's important to create a common understanding and a shared way of specifying the meanings, no? Because typically when people communicate in a natural language, it's fairly easy to disambiguate, the context to understand what we are talking about. However, when we are embedding knowledge in machines, that becomes a little bit more complicated. So it's very important to provide explicit definitions of our terms, of our expressions, of our information. No? This is just, those two are simple examples. The first inspired by the agri-semantics, and is the it's taking into example the term rice, the one that we eat. In this example, we can see that the different professionals might be focused on different aspects of rice, and they might all be valid. For instance, a biologist might be focusing their information system to insert knowledge about the genome, a sociologist about the practices, for instance, the commercial route of rice. A consumer might be focused on the price and quality. Those are all relevant aspects of rice, but are all different perspectives, no? So this is the first example, is we are talking about a rice, but we are talking all about different aspects of rice, no? The second example is about service, and is taken from the literature, from examples from Giancarlo Buzzardi and Nicola Guarino. And the term service that is very much used in computer science, business process modeling, but also for ecosystem services, is often ambiguous. What does it mean? That when we are talking about services, we might refer to it as a contract, so sort of a norm, as an agreement, relationship between parties, or also as an event like the offering or the delivery or the deliver. When we are talking about among people, we might understand the definition of service or what we are talking about rice, but once those information are inserted in information systems, we need to be more precise. Now, this is a little bit of a detour, but I would like to how to say, to clarify. This is actually a simplification on how language works. Also, this is taken from the literature. Typically, we use the language to refer to objects, and to communicate abstract conceptualizations. Now, in this example, we have the potok, that is a species of horse, Basque horse, and that is our referent, is our object, And we might have a conceptualization of it that could be a potok if a horse, and a horse is a mammal. It's very simple. And we might want to communicate, this information. So agents generally human or not human agents, might want to share this information, And the information would be after interpreted based on the conceptualization. However, how can be sure that the conceptualizations of the agents are the same? For instance, both agents might want to talk about the potok, but the first agent is thinking about the potok as a horse, it is a mammal. Instead, the second agent has a different representation of the potok that is their own potok, That is an instance of potok. That is called Frida and has certain characteristics such as height and weight. In this case, we are still referring to the potok, but we're referring different aspects of potoks. So with an ontology, we are able to define an explicit characterization of certain kind of knowledge. For instance, here we have a proto-ontology, we could say, just a graphic. And in this ontology, we are explicitly defined that a potok is a certain kind of species called Epus caballus, and so on and so forth, as you can read. In this case, an ontology could be seen as, and here I will take this definition again from Guarini and Guizzardi, a sort of contract, It's a sort of blueprint that define knowledge. And from that, we can agree or disagree on that knowledge, but at least is explicit, So this is why ontologies are important to facilitate interoperability and semantic interoperability, because it's a way to clarify, and to make explicit information. So now let's, after having seen all these examples from the literature, so why ontologies are important, let's dive into how ontologies and semantics are actually used in ARIES. In ARIES, as Ferdinando and Stefano were saying, basically is possible. The main characteristics of ARIES is to model, and the modeling activity is carried out using a language that is called Knowledge Integrated Language, KIM. As you can see in the bottom, we have a snippet of a model written with KIM. You can see model, IAM, theoretical value of, and so on and so forth. And each of the colored elements that are called concepts carried different kind of semantics. For instance, recreation, as you can see, is in red, and is a process, for instance. So each of those concepts are associated to an explicit semantics that has been previously defined into the ontologies that are underlying the system. So we can say that the KIM, the language, is ontologically based, ontologically found within the ontology of ARIES that is called ODO-IM. That is the most, we could say, we call it like a foundational ontologies, which specify all the semantics of the concepts of KIM. Here I tried to trace a little bit the semantics with the example of demography, human population. Human population is a subject within the ontology of ARIES. Demography, what does it mean? That is a namespace that is associated to a domain ontology called demography. So basically, I know that is a little bit crowded, these slides, but the message that is important is that each element of the language has a specific and explicit semantics that has been already embedded into the system through the ontology. Okay. Now here I tried a little bit to trace all these connections inspired from the meaning of the semiotic triangle, very well known in the literature. To the left, we have KIM, the language that is grounded on the ontology that has been designed and implemented in ARIES, and the language that we used to model is used to query data. Okay, so here we have the connections between the ontology, the language, and the data. This is another view of the semantic layer of ARIES, in which again, here it's basically similar to the previous one, but clarifying a little bit better what is possible to do with the language. It's possible, as we were saying, to model, no? But also to define the new concepts within the domain ontologies, for instance, demography that we saw before, and also to annotate resources. So basically, thanks to the language, it's possible to trace the meanings and facilitate interoperability within ARIES. This is a little bit more, I hope that I'm not too long. I'm good? Okay. It's a little bit more of a concrete example of KIM. And those are concepts, as you can see, geography, elevation, normalize, geography, slope, so on and so forth. All of them are concepts that can be more or less simple. Now, for instance, elevation is a simple quality concept. Why quality? Because KIM specifies different kinds of entities. Before we saw subjects. In green, we have qualities that can be quantifiable or non-quantifiable qualities. And elevation has been defined within the domain ontology geography, as you can see in the namespace. After, we have more complex concepts in which we can associate predicates that specialized concepts or observable concepts. For instance, here we have normalized slope. But we can also create more articulated concepts by combining operators, okay, with concepts. For instance, here we see probability of, that is an operator, and the concept storm, that is an event defined within the domain ontology Earth. And here we have more and more combinations. I'm sure that Ferdinando will dive into this even more into details. But this is to give a little bit some ideas on how the language works and how it's associated with unexplicit semantics within the ontology. So,
so back to me. So you may be wondering why all this incredibly abstract discussion and dive into horses and concepts of horses, etc. It's because it's the most important thing for our system is I was talking about the kind of integration we are pursuing. And the integration we pursue is keyed by semantics. So instead of when you go to Google and you ask for something, you use keywords. So it's in a way it's semantics already, but it's not really structured semantics with meaning and that is validated or validatable. You type your keywords and you get 5 pages of advertisement, after which you might get what Google wants you to think is what you wanted. In our case, what we want to do is to substitute the typical way that scientists address problems, which is how we do things. So a scientist produces a method that allows you to make a particular kind of observations, either a quality or a process or whatever it is. In our case, we would like to enable interoperability and enable, let's say, to be very modest, democracy of knowledge by substituting the what, so the object of interest, the definition, the logical definition of the object of interest, to the method that allows you to obtain that object. Because everyone is able to articulate what they need, even people who don't know how to obtain that. And for example, because every scientist is an expert at something and a complete non-expert in everything else. So a weak problem that requires economics and ecology and sociology and climate to be combined in order to be even described can be addressed by asking the question appropriately and having a machine parse that meaning, understand what the problem is linked to, and then going through the network and find all the conceptual dimensions and resolve them to models that have been written by independent experts that don't know each other. And that's the vision for the system, and that's the reason of this lengthy introduction. So the idea, the way we try, the 4 pillars along which we try to structure this effort are, first of all, semantics, and now you know why. Open and linkable data, and the world is kind of getting there in terms of providing ways to share data and make sure that they're immediately actionable through the internet. It's, let's say, this is the most developed part already in the world at the moment. Open linkable models, which is entirely not developed, which is connecting the information landscape, not only data to data, but also data to methodologies and to models. And that's very difficult because it requires standards that are, I hate the word standards, but they require conventions, let's say, that are much more difficult to get to because the methodologies are so different, and there are, you know, all kinds of models, stochastic, deterministic, especially explicit, agent-based, etc., etc. And obviously, the last part that is needed is the integration. Software technology that can take all these things, use semantics as the key to lead to data and models, and produce those larger scale computational workflows that can address problems that are beyond the abilities of a single individual. So we've produced all of this successfully, obviously, and we are at the moment, it is a kind of a little old view of the system, but we are producing a larger software stack. We have a lot of software development activity, obviously all open source, that contains a number of components. We have here the hub, which is the place where users can be connected to each other. The node, which is where you can start put the knowledge and make sure that it's available to people. The engine, which is the modeling engine that actually takes all these things and does the resolution process and actually builds you the results. And then parts that are depending on the user interface. We have a general interface called the Explorer, basically a blank canvas where you can type what you want, and a modeler, which is an API, which is a modeler's environment where you can actually develop new content for the system and potentially change everything that you find and do things your own way if you want to. But more importantly here, I'll give you an idea of how the system is structured. It's a cloud-based system, so it's first of all not in one place. We do provide at the moment, we're still at the beginning of this adventure, so we are providing a number of servers so that the system is can be used more easily by people without having to install any software or anything like that. But anyone can take all of these servers and install them for themselves. And if we get to a mutual level of trust, meaning that we trust the content in one particular server, we can certify it and it becomes part of the network. And I hope that it becomes bigger and bigger. So we can distinguish 3 main layers that are enabled by this infrastructure. The first one is where the knowledge is put. And the knowledge, by knowledge now, I mean the non-semantic knowledge, the traditional knowledge. So the data, the databases, the layers, the data services, and also models like, for example, the R models or Python models, all served through the network in ways that either are provided already by the original implementers or through adapter that we provide ourselves. Each of those assets are identified by a URN. Something like this is like a URL, but it doesn't have a host name, so you don't have to go back to a particular machine that could be offline at any time. But it's resolved and it can be served by a variety of machines. It's basically a replication strategy. And this kind of URNs are unique, and they identify either a data set or a method or a methodology. There's no semantics yet. This is one layer, it's independent. It's basically the link, the data component of the system. Then there is a semantic layer, which is where what Greta was showing you. So we developed what we call the worldview, which is the set of ontologies, which is developed with communities. Greta is going to do a lot of work with communities to make sure that we have everything that communities need. And then in terms of that worldview, you can create semantic expressions like the one that she was showing, that that are able to be used to annotate the URNs. So we can say model geography, the NASA data SDRM, the first URN you see, which is elevation data, as geography, elevation, and meters. So that way you make the connection between the non-semantic conventional knowledge and the semantics. And there is many-to-many relationships between resources and semantics. It's not every piece of data is born with semantics. You can interpret it in many ways, and that's very important because it enables a lot of flexibility. And the last part is when you actually use this thing. So you go to a system, you make a query, and I will demonstrate that. The query could be as simple or as complex as you want, elevation, or it could be net monetary value of pollination, or it could be an entire process like hydrologies, flows, or something like that. And based on that, the artificial intelligence in the system using the semantics will create what we call a data flow, which is the resolution of your concept in a particular context. So you go to a particular place, in a particular year, you decide your resolution, your scale, if you want a dynamic model or a static model. And at that point, you make a query logically without having to say how. The machine finds out what is the best how for that particular context, and it builds the observations that at that point are alive in the machine, and they represent what the world is now fond of calling digital twins. It could be simply maps, but it could also be agents that have behaviors. The system has a fully specified infrastructure to build behaviors. So that is basically what we provide, and obviously it's not a simple thing. So it took a lot of time to get to a level of usability that is now allowing us to be not too ashamed when we start to involve the people who are outside of the team. But we have this one language, Kim, that Greta was already talking about, and you can see some better examples there. Our models are 5 or 6 lines. They are very, very simple. You can do a lot of things by basically saying the semantics of what you will produce. Then you say you're observing the semantics of what you need, and it's just logical. You don't have to provide data. You don't have to say anything about space and time because the machine will automatically negotiate those things. And you can then connect to, say, a hydrological model, or you do a machine learning model by using the learn keyword instead of model. And you can do models that are agent-based. And if you have different parts of a system that are needed in order to model something, the machine is completely capable of negotiating scale differences between models and data, of using different paradigms and putting them together appropriately, using stochastic models together with models that are not that are deterministic or the agent-based, etc. So in the end, what you get is a much more streamlined way of writing models. And at the end of the seminar, I will show you some examples of something that we do and actually run a query and show you how the machine uses these components, these tiny little components of knowledge to build that response. And I'll show you how it's done the traditional way, which you probably already know, just for comparison, doing the exact same thing. So I'm done. I would give back to Stefano, but can you speak, Stefano? Or
No, you are supposed to give this one.
Oh, I'm supposed to give this one as well. Maybe I will not give this one because then I do a demo, which is basically this. So I will just go ahead. How's your voice?
You do. Okay, I can try.
Try. Okay. We're both very challenging.
I'm sorry for my voice today. So this slide was meant to basically give you a synthesis of what we have been telling you in terms of user workflow. So the idea is always to select a context, a when and where, and then to observe a concept in that context. And then we query the semantic web within the system, and the system produces results that are of different kinds. A data flow, a report, or maps or tables. I will give you more details in a minute. This slide is just to give you an idea about our ambition in integrating data and models coming from very different sources. We have an hydrological model that is quite computationally intensive, and it requires information on obviously climate information, so rainfall, temperature, maximum and minimum, and solar radiation, this information comes directly from Copernicus data sets. So let's say Copernicus in general, all the satellite data producers are looking for ways to give value to this data produced, and obviously using them in models, it's one way of giving values to this data. So that's what we are trying to do, to connect with satellite data producers. And we are in projects with the European Space Agency now for a project dedicated on Earth observation and natural capital accounting. This one is just an example of how easy a data-driven model can be written. So we have talked about semantics, so that part of artificial intelligence. The well-known part of artificial intelligence instead is machine learning. In this case, I'm just giving you an example of using spatial data to build a machine learning model of where to locate solar panels in Spain. So we use as explanatory variable elevation, slope, solar radiation, land cover type, distance to the transmission lines, and the presence of a conservation area. And we say, please learn the suitability for solar panels observing these variables. And we use a classifier that is a Bayesian classifier. And the result, by learning from a data set with a limited amount of points, and then extrapolating to the whole map of Spain, is the map that you see in front of you, which has then been used in other models to locate solar arrays. So what do we offer? We offer, as we said, an interface for non-technical users, where basically users can access the knowledge that is already available in the semantic web. And then on the right side, that is the interface for modelers. So that's the interface for people that want to contribute new information, connect more data, build new models. Ferdinando will show you about this interface in the demo at the end of the presentation. And the set of outputs that can be produced are really of different kinds. I mentioned that there are tables, for example, that are particularly important for natural capital accounting, that is of interest for the national statistical offices. But as geographers, we are very much interested in maps, and the fact that we can produce reports on the fly when the models are run, the fact that every data set that is used is documented with its own metadata in the resource section, and then the data flow diagram, that is basically the diagram of the model built to respond to a query. All of this is offered in order to go beyond the idea of a black box and, let's say, offer full transparency of everything that the machine has done to respond to a user query. Then we have different kind of interfaces, and the most famous one is the interface on natural capital accounting. It's called ARIES for SIA. That is a collaboration with the United Nations. And then, but we can also build very user-specific applications. On the top right, you see one built for the let's say a biosphere conservation area in the Basque Country. And then on the lower part, there is an application dedicated to pollination models, where different kind of pollination models are offered in one interface. And these are just ways to expose the knowledge that has been produced by developers. This is the last slide. This slide is about the natural capital accounting application. And the ARIES for SIA user interface is quite famous. We have around 4,000 users registered, and they are growing by, let's say, 100 every month. And so the user community is really growing up thanks to this project that was started in 2021. and is still in use and expanding. And finally, I must say a new way of using the system is to use it via its own API. So basically having other platforms that can query the ARIES platform machine to machine. So for example, this is a platform by WWF Colombia that is using ARIES models to estimate the impact of green projects in Colombia and then matching them with potential investors in Europe. So I'm sorry for my voice again. I'm finished here, and I give the floor to Ferdinando to give you a nice demo of everything that we said.
Thank you, Stefano. We very much like doing choral presentations where more people speak, but people without voices are a problem. I'm also one of those. I'm a little better than Stefano, fortunately, but so I have to find my coordinates here. Give me 1 second. Okay, and let's take the modeler here. I'll just click on this. This is the same system that you can find online, and don't show again. Please disappear. Thank you. Okay, because I didn't allow the system to find my coordinates because it's not my computer. It's putting us in the Basque Country, a very, very nice place, but unfortunately Venice has a lot to offer, so maybe we should go to around Venice just for the sake of example. I'll just take a little bit of Italy here. So we offer a number of interfaces, and these are the simplest ones. So because the system, as you understand, the semantics is data to the system, and models are also data to the system, and data are obviously data. So that this system can be used for anything you want. It can be used by the industry, it can be used by theoretical physicists, it can be used by ecologists, it can be used by sustainability scientists like us. Obviously, sustainability and climate change, etc., are dear to our heart, so all of our applications are tuned around that area. So the obvious interfaces to produce, in our case, are interfaces that have a geographical and a temporal dimension. And the ones that come to mind immediately are the ones with a map, and a map can be found out and can be used to explore the area of the world you would like to make observations into. The only difference between just a regular map application and ARIES at the moment, which is this application is what we call the Explorer, so it's basically the blank canvas that you can paint on, is to this bar here where you have the elephant that's waiting for you to ask a question. And you have a little menu here where you can set some parameters. You can define a resolution, for example. You look here. We use as a default way to represent space a grid, a raster grid. So you can see that the resolution changes, but you can change it. You can click on that and decide your resolution, or even work in non-grid systems. Anyway, the thing that you can do with this interface is to ask a question. And as Greta was showing you, we are developing a large knowledge base, not very large actually, because for a knowledge base of this kind that contains semantics, it's very important that it's not too large, so it can be learned and remembered. You can just ask a question. You start typing ELE, and the system starts providing me with concepts that come from that worldview. And you can see the colors here. Greta was already describing it. This is an event, election, so the yellow-greenish kind of thing. An elevation, there is a quality that obviously applies to what we have in the computer, which is a region. So the semantics that you see is functional to the fact that the objects you are able to observe must be observable in time and space in a geographical region. And you can have other concepts in the system. If I had a washing machine here, I would be able to observe speed of rotation, for example. I'm just inventing. But even at this level, the query is already functional to the semantics you are implicitly asking the system. And the easiest thing I can ask is something that you normally measure the numbers, like the quality. So elevation, I click on elevation. I have made my choices, or let the machine choice choose the time, in this case, this last year, and the resolutions, probably both fine. And if you say, let's return, the machine looks for a strategy to make an observation of elevation. Very easy, just goes online, finds data, and then builds me the map in the context I was in, and I can click around and look at the elevation in meters, which is the default unit for it. But I can do things that are much more complicated, and I can start building my concept. So I can say, for example, let's say I want the carbon that is stored in the vegetation. I don't have to tell you why that is important. It's one of the things that people ask the most to our system. So that would be vegetation, because it's the realm where the carbon is stored. Carbon, which is the chemical identity of what we're looking for, and then we want an estimate of that. So we want the mass, a weight or something like that in tons, for example. So vegetation carbon mass sounds like the thing to ask. Vegetation. You see a lot of different things. ID means an identity, the identity of what I'm going to ask later. In this particular realm, the biome, the ecological identity is vegetation. Then carbon is chemical identity, fairly easy to find. Cadmium, calcium, californium. We wouldn't find many results, but carbon is a little more interesting. And then mass. Mass will be green, mass concentration, mass murder. Vegetation carbon, mass murder. That's unfortunately an event, so it doesn't really work. So mass, and that probably is a question that the system can already handle with the sky. And in the worst situation, the system will tell you, I don't know anything about this. And you can add the model then. But it does know something. And if I click here, I'm actually looking at the strategy that the system has built in order to make the observation. And this is a simple strategy. This is the default one, more or less, which is the one that has been established by the IPCC as the general method to use, which is going through an enormous lookup table after looking at the status of being burned in the last few years, the land cover type, the kind of region in terms of vegetational associations, the type of continental things, and the fact that this may be a region where the forest is taking over agriculture, which is very important because it's a very different metabolism in that case. And it goes to a lookup table. I can click on any of these things and look at the details of how these things are put together, and I can actually explore it, I can download it. This data flow view is quite fun to look at, but it's also very important for transparency because you know exactly what the system has chosen to do. And obviously these calculations are long finished, and I can click on here and look at the map, and this will be in tons per hectare, and will be red where it's higher, typically forest areas, or blue in the very sad plains where almost nothing is being produced alive. And at the same time, while I make my question, the machine is actually putting together data models, etc., and accumulating documentation and provenance data, etc. So I also have a report that has been written automatically and can print on a PDF, a list of figures, the tables, and a list of the data that the machine has been using in order to do this. And this is still a very simple question. I can add something like something a little more complicated than I like. The blank canvas comes from the fact that I have to type, but because I log in into the machine and the machine knows what I'm more or less interested in because I belong to certain groups, then I can also use the space bar and go up and down and look at things that I can also observe. Net value of pollination is a bit more interesting, a bit more complicated models because it requires knowing whether pollinators are, with the potential for pollinators to pollinate cultures, and net means that it will give me -1 to +1 value, which will be negative when there is less pollination than needed, and green when there is actually more. It could be a useful map for a decision maker to use, particularly in combination with other things. The model is more complicated. Here you see it animated during the calculation. You see that it's taking satellite data from Copernicus services. There are equations, regressions, and lookup tables, all sorts of things. And at the end, you get this will be a pretty sad picture because the populace obviously is all red, but still you have your, and some of the input data are lower resolution, like the temperature data and the solar radiation data from Copernicus. See, 10 kilometers, so they have larger squares. This is not 10 kilometers more, but nominally the data are 10 kilometers. So one obvious place to fix this, to look at solar radiation, for example, which is here, it's like this. An obvious place to fix this would be to provide better data. And you could, at the moment we don't do it this way, but you could have your own data, drag and drop them over their semantics, and then the system will repeat the analysis with the data that you provide. And okay, now you have to use the modeler, the IDE that I'm showing in a minute, but there should be ways to make it easier for people to provide their own data. And the same way you have reports, you have tables, you have your things in here all explained. Thank you so much. So that, sorry. We table today. Now, obviously, this is not the only way to use the system, because this is very easy, because in the end, instead of finding data, finding models, running things, etc., you have to just click, just say what you want. But if you look at the way things work in our system, I'll show you the model that we just ran, the pollination model. It is a little bit difficult to see, probably. I'll make it a little larger, probably, maybe. Okay. So namespace model, let's say occurrence of pollinator nesting, observing land cover type. This is a lookup table, easier. Occurrence of pollinator insect caused by the landscape. It's made by looking at the land cover type, the probability of flowering, which is just another concept, and the occurrence of pollinator nesting to occur, and then you just make a little logical expression here. So in the end, all of this model, which automatically adapts to the environment, automatically resolves these things to data, etc., and doesn't have to mention space, time, looping over grid cells, and all these kind of things. It is about 65 lines, and each of those components can be run independently and can be read by a smart child, because we say model net value of pollination, observing the ratio of pollinated yield to yield. So you can interpolate total yield, but it's understandable, and the occurrence of pollination insects. And when you have it, just do a simple operation. It's readable, it's very simple to understand. While if you look at the way that it is done with, for example, in very popular models here, this is the same model basically in Python, and you have to write all of this, and all of this, and this, and this, and this, and this. I mean, it's very unfair to compare, because this is a traditional model that basically has to provide an algorithm. And in our case, the algorithm is built up by the machine by using the knowledge components, but it uses the semantics in order to make it simpler. You can write the model without knowing if you have data or where you will find the data. You can ask the machine to do that. But even in the situation where you cannot run this model today, you still have a model, and it still makes sense. You can try it with test data, and then leave it there, put it online, and when the data come online, then the model runs, and you don't have to do anything. It will run in space, it will run in time, it can become dynamic automatically if the input data change, or if you add the observable for a concept that is change in a particular variable. If I have change in temperature, which is another model, let's say a climate model, that will automatically be run if your context is temporal, and the system will evolve without touching the model at all. So I'll give you another example here, coming back to the Explorer. When you don't want to use the Explorer, not everybody is comfortable with something like this, you may want an application, a more standard application. So we have a language, the same language you use for agent systems. We can use it to model the agent user and basically drive user interface elements from it, which means that you can load an application like the one, this is the one that we do for the United Nations. Of course, it's full of disclaimers, because the United Nations want the disclaimers. And here you have the same thing. You have the elephant here, and you have your choices. You can still ask for elevation, pollination, etc. But you can also have some facilities here. For example, I decided to use, I asked to highlight the largest administrative region that is contained in my view. I can choose my resolution, years, etc. And here are all the elements of the natural capital accounting standard developed by the United Nations. I was in the technical team as well. And there's a lot of things here like, related to ecosystem services, to condition of ecosystems, to extent of ecosystem. I'll just click on one of the things to look at. So we took Emilia-Romagna here, and we asked her, without even thinking about it, to know how the ecosystems in Emilia-Romagna, the ones that the UCN recognizes as ecosystem using their classification, have changed in the course of these 7 years, 2012 and 2019, which are the default. And we'll take a little bit to calculate, but the output of this will not be only maps. It will be, first of all, a dynamic model driven by all the factors that change the ecosystems. And it will produce a table, which basically a multiple entry table where you can see each particular ecosystem the amount of square kilometers of that ecosystem that were there at the beginning, and how many square kilometers of the other ecosystems they have turned into during that period. And these kind of things are the ones that the United Nations wants to know about all these member countries, so that they can monitor the status of the ecosystem services and natural capital in the world. Now, that standard that was approved in 2021 is very difficult for countries to meet, because there is a lot of details and there's a lot of requirements from data, from people who know the issues, so they need an office for that, they need to work. So some countries are very good at producing this, like Holland or others. Other countries are much less good at doing it because they have less resources, because they don't have good data, etc., etc. Now we can produce the baseline accounts for all countries in the world and submit them to the actual countries and tell them if they approve or not. If they don't, they can tell us why they don't, and we can know something else. And because all the choices that the machines makes are contextual, then at that point we can change the algorithms so that they best reflect the vision that each country has of these aspects of the standard in their own situation. So as you see here, some of the variables are getting a little clock, which means it's changing through time. It shouldn't take a very long time, because then we have data that are kind of unevenly distributed, so we can see it end, and then I'm done with my presentation here. But ecosystem type, which is the variable that it counts at this point, and is going to be summarized in the final table, is you see here, there's basically some ecosystem that the UCN have decided are the ones to count. You can click on them and see the categories. And as the system moves on, we will compute this table, and this table will be automatically in the format that the United Nations requires. This is just an application, and we have tested with all the helps and the user guides and all the UN disclaimers, etc., etc. You can download everything. It's much easier to use than the raw naked Explorer. So less power, but you still have the Explorer behind all this. So this is one example, but we can build applications for things that are completely different from there without actually straying from our normal mission, because what we do is purely providing a way to connect meaning to results, going through human intelligence, going through human knowledge that has been provided by different experts in different categories, in different things. They don't have to know each other. They don't have to talk to each other. And in the end, we produce a whole lot of results. We have 4,000 users at the moment. The system gets a lot of use in just the online part. We are monitoring now. There is a whole lot of people using it. And we have maybe 500 data layers total, but not really that many, maybe 150 models. And the interesting part about integration is that integration grows multiplicatively, because if you add one new piece, that new piece is able to connect two more that were not integratable before. So the value of 10 pieces of data is 10. Adding one doesn't make it 11. It may make it 100. And it's a very powerful metaphor for knowledge, because that's what it is. So you have the ability of providing a lot, but just adding your own bit of knowledge that eventually will contribute to building higher level understanding. That's why the ambitious goal of saving the world using this technology. I firmly believe that using semantics intelligently is the way to go to solve the problems that we aren't even not able to address. We aren't even able to conceptualize, because the book has to be read, and the book is there, but we are trying to make it readable by using semantics. That is taking a little time more than I.
Maybe you can show the engine online how to access it.
Sure, of course. From the start. Okay, so you guys can go anywhere you want. This is one of the many pages where we can get started. And I never use this by the way. So
the modeler, and this is the online.
Okay, so you can use the system in two ways. Maybe this hasn't been said. You can use the system on your own machine. Doesn't mean that it's limited to your own machine. It still goes online, but the computations happen on your own machine, which is very good if you are experimenting, particularly because you get the modeling interface, the one I was showing before, this one. And you are able to change things that otherwise would come online and would be read-only. So you can make a lot of experiments. And then you have total freedom. Or you can use the system online, which has the ability of being used without doing anything, basically. So I can just put my login, and you can register for free. And then you get the same Explorer or the same applications that you can show. Let's do this. Remember me? No, please. Don't. And it gives you a choice of which applications you want to run. So if I go with the Explorer, then I can start the ARIES for C, and there may be eventually other applications. ARIES for C is available in a lot of languages. So maybe I will do it in Chinese, but I went back for some reason. I don't know why. So I don't want to put my password another time. But anyway, now I can show you the final. Is this one? No, you have double that. I have twice. Okay. So it's also smaller resolution here, but so it's pretty hard to read. But this is the table that we have asked for. So basically, we can take cropland, and these are the same ecosystems on the rows, and you can follow a row here. So for example, 20 square kilometers, 21 square kilometers of cropland have turned into forest, in temperate montane forest in Emilia-Romagna between 2012 and 2019. These are very useful outputs for both decision makers and as a statistical. And you can ask for this, you can ask for conditions of forest, you choose your indicators, you can use any of these, NDVI, drought severity, etc. You can look at account for crop provisioning, climate regulation, storage of carbon, sediment regulation. We even have some monetary accounts that we try to stay away from as much as we can, because they are very hairy to calculate. But when we know how to do it, because there are price tables, etc., we do it very happily. And that's where I will stop. But I'm hoping that you see this as a beginning, because that's what it is. We are trying to provide a methodology that is much more general than the applications we've been showing. And now at this point, I think we are very happy to take your questions, and we try to speak the least possible, or make Greta, who seems okay with her voice, respond to all of them. But anyway, thanks for the attention for the time being.
I would like to thank FEEM for the invitation, and also to notify everybody that we are in a collaboration with the group of Venice. So there is going to be a dedicated application written in this language on exposure and the risk of different kind of hazards. So that's where we are starting, and that's our collaboration.
So thank you for your presentation. I hope you can hear me online, because we are using the same microphone. Thank you. And so while we wait for other possible questions online, we have two from the audience here. The first one is it possible to make machine learning and machine reasoning interact in some ways in order to overcome the relative disadvantages of those approaches separately?
Sure. Yeah, I'll probably take this one. Absolutely. Actually, we really do. I mean, for example, many of our models are machine learning models, and they are connected by machine reasoning. So that's the easy answer of what we do already. But there is a lot more that you can do. For example, machine learning is ideal to improve the system through time, because the system monitors the results, it gets feedback from users, etc., etc. And one of the core elements in the system is what we call the prioritizer algorithm, which is basically when you ask for a concept, the machine looks for models that apply to a context. It may find one, but typically it may find more, also data sets. So it needs a strategy to rank those potential responses according to which one is the best for the context. And obviously that's complicated. We use several complicated technologies. So the technology we use is a mix of objective and subjective indicators, which we mix using some multi-criteria algorithms in a prioritized moving mean. Is very complex, and it's obviously an area in evolution. But when that is done, it can be validated, and through machine learning, we can actually improve that process so that the machine gives better and better responses. It's not the only way that we inform the prioritizer, but there are also ways that are more based on human choice, because even the same semantics for different groups can mean relatively different things. So we give people the ability of following groups or institutions so that we know that they trust certain people, and this is outside of the learning part, but the prioritization is the obvious place. So we have nothing against the machine learning, but we have a lot against machine learning when it's used to control minds, which is basically or to sell products, which is the same, which is basically the same, the current usage. Also, one thing that I like a lot is that machine learning techniques are becoming the biggest users of energy on the planet. It's even worse than air travel. And it's getting worse and worse. You see what happened with ChatGPT, which basically serves no purpose at the moment. It's only a game, but it's a very, very, very lucrative game because people will use it, etc., etc. Everybody's trying to build a clone of ChatGPT. Every training of something like ChatGPT costs 2 million and consumes the amount of energy produced by a nuclear power plant. And it's getting worse and worse. Every year we get like a tiny little benefit of 0.5% control of emissions. We emit a little bit less, and then we use 30% more to do stupid artificial intelligence that serves no purpose. This stuff is incredibly cheap to run. It's just the reasoning on an ontology, which has to be very carefully designed so that it contains a minimal amount of terms, is so cheap compared to the other, and produces, allow me, so much more, that we feel we are on the right side of artificial intelligence. It doesn't mean that machine learning is to be abandoned. Things like reading an MRI report or an X-ray, machine learning is so amazing there, because I mean, you can have 3 radiologists and they're all good, but one will make a mistake, the one will not see something, and the third will see everything. Now, with machine learning, we can make all 3 to make sure that they see whatever it is there to read, and then they can talk to their colleagues and do the right thing. But building proteins for immunotherapy, machine learning is fantastic for that. But even those are like a 0.1 per 1,000 of the usage of energy that the world is doing on machine learning for purposes that are basically just consolidated the position of power that corporations have. So yeah, it's a long answer, but I do believe that there are, both of them are very incredibly useful, and we are definitely planning to use both of them.
Thank you for your answer. And we have a second question. In order to build a model, is it possible to specify concepts according to different schools of thoughts in economics? For example, the concept of capital is not the same for neoclassical economics and Marxist economics. What do you think about this?
I think a lot of things. Greta, do you want to take it, or can I?
Maybe you can start and I can integrate.
Okay. Yeah, this is a very, very common question we get, is that by using ontologies, we basically subscribe to a school of thought. And in a way you do, but in truth, what we have found is that it's the use of ontology in this way. We don't conceptualize school thought systems. We conceptualize observations and nothing else. And one of the important part of the foundational ontologies that we use is that it's phenomenological. It doesn't have any pretension of actually conceptualizing the world or even concept at that level of sophistication. So in all of our experiments, the potential controversial role of using ontologies has been proved to be not an issue. So the answer to that specific question is yes, in terms of being able to do it, and probably no in terms of whether it's worth doing it. We try to our concepts are only things that can be observed. So we don't have a concept called capitalism. We have we have monetary value, and then what we have in the system is context. and context is much more important. The context is not limited to space and time. Context can also be ideological, it can be opinions. So you can add to the scale of the system. The scale, basically, you operate on a topology, right? Or a topology of space that could be multiple, can be a grid, can be vectors, can be, and definitely has an extent and an internal structure. And the same for time. You have an extent, you may have time steps, you may have points of reference in time, etc. That scale, which is the basically Cartesian product of these two dimensions, these two topologies, can also include dimensions that are conceptual. And I think that's the proper place to put something like that. Instead of having them in the ontology as the observables, and then you have to refer to a school of thought in order to explain what you are observing, it's much better to use whatever conceptualization you are, particularly if the conceptualization affects the measurements and affects the way you look at the world, it's much better to use that to build the conceptual dimensions into the scale, so that the system can automatically take care of not only one opinion, but also different ones, and potentially compare them, because your scale is space, time, and opinion over Marxism or capitalism, and potentially other dimensions. The system is fully set up to do that. We haven't done it, never. There's never been a need in order to build these applications. And it is very possible that in one day we have an application that actually need to incorporate a different schools of thought in order to be completely representative of useful results. We have no experience with that, but it will be interesting to experiment. But I think the place for that, it's still ontologies, but at that point we don't need to conform to our foundational ontology, which is meant only for observations. You can bring in different ontologies of your choice and use them to build the conceptual dimensions that you add to the scale, and that will be the responsible way to do it.
Thank you very much. I don't know if you want to add or.
I think that pretty much said everything very clear.
Perfect. Thank you very much. And the following question is, when dealing with environmental issues, how does ARIES consider economic assumptions?
Aha, this is yours.
Economic assumption. I mean, we, in general, for example, all our applications in ecosystem services are not monetary fixed, meaning that we don't subscribe to any fixed monetary technique. We use all of them. And for example, for the ARIES for SIA application, we have used the monetary techniques that are suggested by the standard protocol of the United Nations. I mean, we definitely, for us, it's just a matter of choosing the appropriate method for a certain topic, but it's not that the ARIES chooses anything in particular. We can deal with all of them. But as Ferdinando said, we try to stay away as much as possible from monetary valuations, because it's very little agreement out there on how to do it properly. So we tend to keep biophysical assessment more in our, at least in the ecosystem services applications.
I mean, it's still another, it's just another model in the end, but I spent 15 years with Robert Costanza's group, and the only thing I learned from there is that these things cannot be done right. They can only be done wrong. So I'm not sure if I want to spend the rest of my career struggling which is the least wrong assumption. And I think it's better to find them common ground and uncontroversial use cases. In the end, most of the rest is academic discussion. But it's good that we work with the international institutions because they have task forces on this. So in the end, they will produce something that is the least wrong. It will be very wrong. We'll implement that, and then if you want another, they just put together another task force.
It's better to receive the guidelines from higher institutions than us.
Yeah. Thank you for your answer, and these are all the questions.
Excellent questions, by the way. Thank you.
And okay, perfect. I think we can close the meeting. Thank you all for being here. Okay, bye.
very much for inviting us.
Thank you very much.
Thank you.
A pleasure. Ah, wait.